Welcome back. So, in the last class we have seen that how we can using the conservation equations of mass, momentum and energy, we can connect the downstream, that is the bound state of the gas with respect to the unbound state, that is upstream state of the gas, whereas with the reference we are defining upstream and downstream with reference to the chemical wave which separates the upstream and the downstream states. Okay, and we are talking about essentially premixed combustion, and we have found that there can be two states in which this chemical wave can propagate, and one is the state in which it propagates at a subsonic speed, and another is a state at which it propagates into a supersonic speed. And when it propagates at a supersonic speed, we call it a detonation, and we have pressure rise, density rise across the wave, and when it propagates at a subsonic state, we have pressure drop, density drop across the wave. So, for all practical purposes, all modern engines use deflagration or flames, either non-premixed flame or premixed flames, and so far we have not used detonation as such, except there are some developments like a pulse detonation engine or a rotating detonation engines, but these are very much under development and that has not been practically realized yet. But there is still a lot of interest in the topic because it allows you to increase the pressure downstream of the wave, whereas across a deflagration you have a pressure drop, and that leads to the loss of efficiency for a combustion engine. Okay, in the whole thermodynamic cycle you lose some efficiency for that. So, now we talk about the deflagration wave, and that is essentially a laminar premixed flame. So, we have seen that in the hydrodynamic we can have a very different descriptions or descriptions of the premixed flame at different levels. Okay. So, we can look into hydrodynamic level or the Rankine-Hugoniot level, where essentially we have seen we consider essentially the whole flame, the whole structure to be a sheet, where we do not really resolve the structure of the sheet, what happens inside the flame or how does the chemical reactions happen, we do not care. We are only happy with the uniform upstream and downstream states, where we have seen that this is our flame, okay, and this is our flame, and this is the downstream state, and this is the upstream state, and so we have upstream we have YU, that is a mass fraction of the fuel unbound, and this is the mass fraction of the fuel bound, which is equal to 0, and this of course if it is a stationary wave, that is if the wave is not propagating with respect to our coordinate system, then of course it invariably implies that there is a flow into the wave, which is that is unbound reactants are flowing into the wave at a velocity of UU0, or which is equal to the SU0, or the burning speed or the burning velocity of the flame speed of the of this flame. So, this is the flame sheet limit. Okay. So, it means that that we are viewing the flame for a very far distance, where you are not really looking into what happens inside this sheet. But then if you zoom in, if you put a magnifying glass and zoom into this sheet, okay, and what you see, what happens is that sheet essentially has a finite thickness. It has a diffusion zone or a preheat zone where the temperature actually increases. So, if this is unbound gas temperature, this is a bound gas temperature. So, there is a region where the temperature sharply increases, and this diffusion zone is characterized by this thing which is this LD0. Okay. And the reaction zone is essentially frozen due to large temperature TA, and we again consider this reaction sheet limit, where essentially your because the reaction zones are happen in a very small distance because of the large activation energy that we have already seen. But there is also a mass diffusion zone where this species does not change abruptly, which is not possible in reality because everything has to change in a gradual manner. It only depends in a perception of length scale. So, when you zoom into this in this flame sheet, you see this preheat zone and the diffusion zone, but you still our magnifying our zooming capacity is not enough to look into the reaction sheet. But if you zoom in further, okay, you will see that there is also a reaction sheet which also happens over a small and a finite distance or a finite length. So, this additional additional reaction zone, this LR, which is this thickness, that is the temperature increases like this, okay, that species decreases like this, and this is the reaction where the reaction is peaking, and that happens over a length of LR0, and LR0 is because it is a standard conditions we are considering, and this is the LD0. Okay. So, this is the flame structure, the 1D flame structure in the x direction. Of course, in a gas turbine engine you can have a flame like this, that is these are the swirlers. You can have a flame like this in a actual gas turbine combustor. So, basically then in that, if you this is our x, so or this is our x, direction. So here what we will see that whatever happens here in this thing is essentially is happens like this. So the temperature increases like this, the species decreases like this. So this we need to understand this flame structure to essentially know what happens actually in a how the flame structure in an actual engine behaves. So this idealized version is very important, but once again to understand that this thing is essentially an element. This flame structure that we see here can be considered as a building block or an element of the complicated flame structure that happens in an actual engine. Just like the chambered flame is actually an element of the complicated flame structure that can happen in some other non-premixed combustors. So these type of understanding is very important. Okay, but now itself, even going into the details, we can now understand that because the activation energy is very large, your LR0 must be very larger than LD0. So this is one important thing. So another thing is that system is of course conservative, and your F, that is the burning flux or the mass flux, rho u is equal to your rho u 0, that is the upstream velocity, and your rho b 0 u b 0. The 0 comes because it is the reference conditions. This is also the reference conditions. It is the planar laminar flame speed, this u 0 that we will see. Because if in a state we are attached, it is just coordinate transformation. So if our flame is steady with respect to our coordinate system, then it means that the flow is coming, the burnt mixture is the unburnt mixture is approaching it at a velocity u0, whereas if the unburnt mixture was our reference flame was attached to the unburnt mixture, that is the unburnt mixture was fixed, then of course the flame would have propagated into the unburnt mixture with the same velocity u0, but then we will call it SL0. So essentially u0 is equal to S u0, this unburnt gas thing, unburnt flame speed that we see. And another thing is that this is very important. This comes from the energy conservation. Your CPTB0 minus TU0 is equal to QC times YU. Okay, that is, this is the mass fraction, and this if we just integrate across, you will get this, and this gives you the flame, what the flame temperature would be. This is essentially the adiabatic flame temperature for the stoichiometric, not for the stoichiometric, but for the equivalence ratio of the mixture that is being considered. So then we need to just understand the difference between the temperatures for the non-premixed flame and the premixed flame. So if we consider the non-premixed flames, here we in this thing we will on the left hand side we will consider a non-premixed flame, and here we will consider a premixed flame. So the non-premixed flame was like this on this, both are 1D variations. So this is 0, this is L, this is X. So the flame was somewhere here. So this was your temperature T0, TL. This was YF0. This is just the previous thing that we did. Nothing can survive, no fuel. This is the fuel mass fraction on the left hand side, because it can contain some inert nitrogen also, and no fuel can survive beyond the flame. This is the flame location XF, and this was your YOL, mass fraction of the oxidizer on the L on the right hand side. And these things were linear because it was just diffusion controlled. Okay, and we saw that this is just by coupling function, this becomes the solution of the Laplace equation del 2 beta I del x square is equal to 0, and the temperature formula that we obtained was this. Okay, and so what happened was that, so this was the heat release and so and this is a fuel mass fraction. So if we consider 1 kg of fuel mixture, okay, so this was the amount of heat release. So this 1 kg of fuel mixture was used for heating up 1 kg of the heat release from this 1 kg of the fuel mixture, which contained YF0 kg of fuel, was used for heating up 1 kg of fuel mixture, and this we found was exactly the stoichiometric amount of oxidizer, required for stoichiometrically burning the 1 kg fuel mixture or YF0 kg of fuel mixture. This was the thing, right. So this is what we had obtained exactly in the previous class. So as a result of this TF, what we obtained was the adiabatic stoichiometric adiabatic flame temperature for the system. Okay. So now if you say that YF0 is equal to 1, so just to show you back, this is how we obtained this. If we just go back to the previous class in module 6, this was the thing that we obtained. So this was the temperature equation that we had. Okay, and then when we substituted substituted this thing into the XF that is here, that is the XF value that we obtained here, and then this is the temperature value that the temperature formula that we got. Okay. So and this thing was the exactly the amount of this is exactly the amount of the air. This is we obtained in this manner, that is I'll just go little bit briefly over this because this was so important. That is 1 kg of fuel air mixture contains YF0 kg of fuel, right. Now for stoichiometric burning, whereas this sigma 0 was nothing but W0 times nu 0 double dash minus nu 0 dashed divided by Wf times nu f double dashed minus nu f dashed. So for stoichiometric burning, W0 1 kg for stoichiometric burning 1 kg or stoichiometric burning, sorry, this is Wf times nu f double dashed minus nu f dashed kg of fuel needs this W0 times nu 0 double dashed minus nu 0 double dashed oxidizer, oxygen, right. So YF0 kg of fuel needs W0 times nu 0 double dash minus nu 0 dashed divided by Wf times nu f double dashed minus nu f dashed kg of oxygen times W0 F0, right. So this is nothing but, so for stoichiometric burning YF0 kg of fuel needed sigma 0 times YF0 kg of oxygen, right. But 1 kg of air or oxidizer mixture contains Y0L kg of oxygen. Okay. So sigma 0 times Y F0 kg of O2 can be found in sigma 0 YF0 divided by YOL kg of oxygen mixture. Alright. So, as a result, this thing was exactly the amount of oxidizer mixture, that is air, required for stoichiometric burning. So, this, you see, the thing is that if we just remove all these things, the thing which comes out is that this heat release, okay, this heat release goes on to support into heating up 1 kg of fuel mixture and exactly the amount of oxidizer mixture required for stoichiometric burning of this fuel mixture. So, the burning that is happening is stoichiometric. Okay. So, when the burning that is happening is stoichiometric, then the flame temperature reached is nothing but the adiabatic flame temperature. So, here the most common situation is that the fuel does not contain nitrogen, say it is pure fuel. So, here this QC is equal to, then it means your YF0 is equal to 1 if it is pure fuel, that is there is no oxidizer, but of course, the air will contain some nitrogen. So, then it means is essentially QC is equal to TF minus T0 plus sigma 0 by YOL times TF minus TL, right. So, this temperature thus obtained is the phi equal to 1 adiabatic flame temperature. Okay. It is always at the peak, this flame temperature. On the other hand, if you consider the premixed flame, that is this structure, this is your flame sheet, this was also your flame sheet where your XF here is. So, here your fuel and oxygen mixture are premixed, right, and this your fuel mixture is YU. 1 minus YU is equal to your essentially your air mixture or is the oxidizer mixture like this, okay, and your species is reducing like this. Here is your flame sheet, okay, thin. Okay. So, here the temperature thus reached is Cp times Tf minus Tu, or we will say call it Tb minus Tu is equal to QCYU. Okay. Now, you see here on this side your YF0 you could set it to 1 whenever there is no nitrogen in the fuel, which is the most likely the case, right. So, then the fuel mass fraction is equal to 1, it is pure fuel that is going out. So, when a pure fuel the flame temperature is the phi equal to 1 adiabatic flame temperature, but this YU here you see it can never be equal to 1. The reason? The reason is that 1 minus YU is equal to your mass fraction of the oxidizer or the air. YU can never be 1 because this is mixed with the oxidizer. Okay. So, it is always less than 1. As a result, this temperature is still the adiabatic flame temperature because there is no heat loss, okay. But this is the adiabatic flame temperature at a given phi, which is a function of your YU, okay. So, depending on the stoichiometric, depending on the equivalence ratio, now you can essentially control your TB or TB0. So, that is the difference here. The difference is that here you cannot control TF. TF is always the stoichiometric adiabatic flame temperature as long as it is a pure fuel, okay. On the other hand, here just by changing the stoichiometry, if you just put in less fuel or and more air, you can control the flame temperature. So, that is why premixed flames are very attractive in any engineering things. It allows you to engineer the flow inside, or it allows you to engineer the product composition and the product temperature, also the composition, because you see that temperature is very important. You have seen that when you consider this thermal NOx production of the Zeldovich mechanism, this N2 could be split up only at very high temperature, right. So, for or vice versa, whenever there is high temperature, this N2 can be split up by an oxygen, right. So, you always want to reduce emissions, unless there is some other pressing needs, you always want to combustion to happen at a temperature about 500 about 1600 1700 Kelvin. So that you can do readily with this premixed flame, okay, where you just control the equivalence ratio and then you get the low temperature. Of course, there are things associated with it, like that is where the challenge comes, like flame stability, thermoacoustic oscillations that we have to deal. But here, unlike in a non-premixed flame where you cannot control the adiabatic flame, you can control the flame temperature as long as your fuel is pure. Here, because it is mixed with the air, you give in less fuel, you get less temperature. You can appropriately control the flame temperature, and you can also control the things like emissions, etc. So that is the advantage. So then we go into the flame characteristics, that is how much one very important characteristics to note is that if you were considering this so if we were considering the premixed flame structure, where the reaction zone was like this is your temperature TP0, this is your TU, this is your LR, and this is your LD, LR0, LD0. So if you want to find out what is the relation between LD0 and LR0, we want to find out this thing LD0 by LR0. Okay. So then we have to find out basically LR0 what is it. LR0 is or we go into this simpler description, that is in the flame sheet limit, that is this description, where we consider there is a finite thickness, but we do not resolve the structure. So this is your basically then your is LD0, this is your LR0. So then by similarity of the triangles here, we can say that this is your TB0 and this is your TXF minus, that is just, and this is basically your reaction zone, okay. And so this is your TXF minus, XF minus is just prior to the flame, okay, and this is your say 0. And so you see this is the temperature that we are talking about. So the temperature reaches after combustion reaches the Born gas flame temperature, which is the adiabatic flame temperature at that given equivalence ratio, and there is a small thickness which is the reaction zone thickness LR0, and just before the reaction zone thickness the temperature is slightly smaller than TB0. So we need to find out what is the ratio of this LR0 by LD0, that is the reaction zone thickness to the diffusion zone thickness or the preheat zone thickness. We need to find out what is the we will apply the similarity of triangles. That what we will do is that we will do something like a TB0 minus TXF minus divided by LR0, that is this difference by this ratio is essentially equal to TB0 minus TU, TU is here, TU divided by LD0. Okay. Even though this considers a little bit of the diffusion zone, strictly speaking the diffusion zone is here, but since LR0 is smaller than LD0, this equation holds. So for that we need to find out this thing, that is TB0 minus TXF. So how do we find that out? We find that out by saying that TB minus TXF is essentially proportional to W divided by dW dt at TB0, and that is given by, whereas if we say that this W is proportional to, of course there are other things also, that is W is proportional to e to the power of minus TA by T, we will consider that we will say that we just take this derivatives and it find that it essentially becomes ratio of TB squared divided by TA. Okay. So whereas TB square is a Born gas flame temperature and TA is the activation temperature. So we can just find this out, and then we apply this thing, that is LR0 by LD0 is essentially delta T across the reaction zone divided by delta T TB minus TU, and then this we substitute this here, and we get LR0 by LD0 is essentially equal to TB0 square divided by TB0 minus TU by times TA, whereas this thing is a very important quantity. And that is called the Zeldovich number. Okay. So, this guy is called the Zeldovich number, and it is a very important quantity, and the Zeldovich number is always very large. You see that in the bottom you have a very large quantity which is TB0 square. On the upstairs, there is on the numerator you have TB0 minus TU, which is proportional to TB0, but since TA is much larger than TB0, you see activation temperature is much larger than TB0, that is a bond gas flame temperature, which comes from the kinetic considerations, that why your activation number should be large, because that is the only a small fraction of the molecule should be excited to start the reaction. Okay, so this TA is very large, and they should have a very large energy, and as a result of that the Zeldovich number is very large. Okay, whereas the inverse of this is much greater than 1, whereas 1 by Zeldovich number should be much less than 1. So, essentially we see that LR0 by LD0, which is equal to 1 by Zeldovich number, that should be much smaller than 1. So, this is the deal, this is the consideration that LR0 by LD0 should be much smaller than 1. Now, we can go into balance of the diffusion and the convection and the diffusion flux balance in the preheat zone. Of course, you see that in this structure, that in this zone of LD0 there is no reaction, this W equal to 0, or in this part, that is in this region, this is how the temperature increases. Okay, so, in this region we can consider your reaction rate, the species independent reaction rate or the species production rate, that is equal to 0. Okay. So, that is equal to 0, and as if that is so, then essentially your this is just like the previous relations that we used while deriving the coupling functions, that even the flame essentially means reactions, but because the Zeldovich number is very high, because the not the Zeldovich number, because the Arrhenius number is or the activation temperature is very high, as a consequence of that your Zeldovich number is very large, and as a result your reaction zone thickness, that is the LR0 where the reaction happens, is much smaller than your preheat zone thickness. So, in lot of the flame actually there is no under this assumption there is no reaction happening, it is only balance between diffusion and convection. So, if there is balance between diffusion and convection, we can just consider this equation, that is say anything, we consider the temperature equation, the one dimensional temperature equation, which is F0 times Cp dt dx minus lambda d2t dx square is equal to 0, right. So, then it means that then if we do an order of magnitude analysis, we say that this is represented by F0 Cp, where this happens is essentially delta T, which is equal to Tb minus Tu divided by LD0, that is the diffusion length, and that should be proportional to or have the same order of magnitude as lambda times delta T divided by LD0 square. Okay, then this cancels, and your LD0 is nothing but lambda by Cp times 1 by F0. Okay, or your F0 is nothing but lambda by Cp times 1 by LD0. Okay. So, this is a very important relation you see, or you see that, or we say that LF0 times LD0 is essentially proportional to lambda by Cp, which is your thermal diffusivity divided with the specific heat. Or of course, F0 is essentially equal to your rho u times SL, or you can also write that SL0 times LD0 or SU0 times LD0 is proportional to lambda by rho Cp, essentially is equal to thermal diffusivity. So, SU times LD0 is equal to constant is equal to thermal diffusivity, and that arrives just from the fact that in the preheat zone it is just a balance between your convection and diffusion, and then there is no reaction at that place. Okay. So, that is the consideration that with that we can arrive at this. Now, of course, we have to whatever flux goes in, whatever F0 goes in through this convective diffusive zone, that must also be reacted. Okay. So, if you remember the dimensions of the reaction rate, and then we can also relate your F0 essentially to this thing, that is the WB0, the species production rate at the bond gas temperature. times LR0. So that is how you basically dimensionally you connect with the F0 with the reaction rate. So the assumption is that the reaction mass flux entering through the flame, that is Y0 times Fu, okay, which is equal to the reaction flux through the reaction zone, which is Y0 times Wb0, because that is a species consumption rate, times LR0. So when you equate these two things, that is Yu times Fu0 is equal to Yu times Wb0 times LR0, this cancels, and your Fu0 is nothing but Wb0 times LR0. Okay. So now of course what you can do is that you can relate this guy with this guy. Okay. What you can do is that you can just multiply these two things, and you will get F0 squared is equal to lambda by Cp times Wb0, that is the reaction or the species production consumption rate at the barn gas temperature, times LR0 by LD0. This is a beautiful relationship that emerges, and by very simple considerations, just by considering the species flux, just by assuming that the species flux that travels to the preheat zone, that is a convective diffusive zone, is also has to be consumed in the reaction zone. So from that thing this emerges, this relationship emerges, and do you see what it is? This is nothing but lambda by Cp, that is the thermal diffusivity of without the density, times W0, and this is what LR0 by LD0 is nothing but 1 by Zeldovich number. Okay. So then this thing emerges that your F0 square is that is a the flux, the burning flux squared is essentially lambda by Cp times Wb0, that is Z is Zeldovich number, or you can write it like this, your F0 is essentially square root of lambda by Cp times Wb0 and by times Zeldovich number to the power of 1/2. Okay. So here you get plenty of information about premixed flames. Okay. And also you can of course find out the LD0 is equal to lambda by Cp times Wb0 times Zeldovich number. But this thing is, as I said, that the burning flux or the burning velocity is the most important property of a premixed flame, and from this very simple consideration itself you can get a plenty information. One has to always remember this, that is F0 square, F0 is essentially equal to square root of lambda by Cp times Wb0 times Zeldovich number. That is the thing, which means that you see this F0 is essentially the geometric mean of lambda by Cp and Wb0. So it means that in a premixed flame your lambda by Cp and Wb0 both are equally important. Okay, both diffusion and reaction are very important, and that is why the premixed flame is much more sensitive to chemical reaction mechanisms and everything. Whereas in a diffusion flame, which is basically diffusion control, as such you have seen that your F0 is essentially proportional to lambda by Cp. Okay, in a non-premixed flame your F0 or F in a chamber flame you have seen that it was proportional to lambda by Cp times the velocity the species gradient, etc. But here it has, this has r to the power of 1, here it is to the power of half. So of course here the diffusion importance of diffusion has gone down at the cost of chemical reactions. Okay. But this thing has to be always remembered. This is the first order calculation, a very basic calculation which yields this thing, this analysis, but it's very important. We will go into more sophisticated analysis later to arrive at this again, but this itself gives a lot of information. It says that F0 square, that is a burning flux square, burning flux is essentially proportional to the square root of the thermal diffusivity without the density, and is also proportional to the square root of the reaction rate at the barn gas temperature, and also inversely proportional to the Zeldovich number to the power of half. So all these things gives a very important information, and which is now this F0 is now used to close actually the Rankine-Hukunian relation, where you see mu was not specified. So this essentially, this result shows three fundamental quantities governing the flame response. Lambda by Cp is a measure of diffusion, Wb0 is a measure of reaction, and Zeldovich number is a measure of activation, because Zeldovich number, you see what it was, is essentially Ta times Tb minus Tu divided by Tb0 squared. Okay. So this is a measure of essentially the activation energy and the exothermicity Tb0. So these three things shows how the premixed flame actually responds. and as such the response of premixed flames is more rich in terms of response rather than a non-premixed flame because of these things. So, as we have seen that here your non-premixed flame the burning flux was proportional to lambda by Cp, which says it was diffusion dominating pre-only diffusion, and here your premixed flame your F0 is equal to lambda by Cp to the power of half, and where because your reaction is also equally important, is also proportional to the power of half. Okay. So, as a result what you have seen is that F0 is essentially proportional to square root over lambda by Cp times W0, or the propagation rate is a response of the flame, which is the geometric average of the diffusion and reaction rates, which are the driving forces in the forming the flame. And here of course we can say that F0 times LD0 is equal to lambda by Cp, which depends only on transport, whereas F0 by LD0 is equal to W by 0 times Saldovich number, which depends only on reaction. Okay. So, to end this discussion, that is flame characteristics, as we have seen that there are only two controlling processes, that is diffusion and reactions, and the flame characteristics are described by independent relations, which can be expressed in 3 different ways to convey different messages. So, if we just consider the balance of the processes, that is the balance of the convective and the diffusive terms, or the convective and the diffusive fluxes, you obtain this F0 is equal to lambda by Cp divided by LD0. Whatever is flowing, this flux has to be consumed if there is complete combustion, and of course which is the case, and F0 is essentially WB0 times LR0. LR is the reaction zone thickness. And then we can combine these two to find out explicit relation for the responses, whereas F0 square is equal to lambda by Cp times WB0 times by Zeldovich number, and this LD0 square is essentially lambda by Cp divided by WB0 times Zeldovich number. And when we do the explicit relationships, we can find this sort of things by considering only the diffusive properties or the reactive properties. F0 times LD0 is only dependent on diffusion, whereas F0 by LD0 is only dependent on reaction. So, then the thing comes that how does your F0 or SL depend on pressure? Now, we know that your WB0, because it is a law of mass action, where because WB0 is essentially governed by law of mass action, that is the reaction rate should be proportional to the product of the concentrations of the raised to the power of the stoichiometric exponents, and we can also alternatively write it as this concentration is the essentially proportional to the pressure. So, we can write it as WB0 essentially to the power is proportional to P to the power of n, where n is the reaction order. Okay. Now, we have already known that F0 is equal to lambda by Cp times WB0 to the power of half, whereas WB0 is essentially P to the power of n. So, this gives you a P to the power of n by 2 dependence. So, F0 is essentially P to the power n by 2. Now, SU0, which is the burning speed or the flame speed or the burning velocity, SU0 is proportional to is essentially this rho u times SU0 is equal to F0, that is a flux. So, this is equal to this. So, it essentially becomes once again P is equal to rho RT. So, your P rho u is essentially proportional to pressure, that is upstream density, but there is no temperature variation, that is we can do this. So, F0 by P. So, then this also gives you a, so this part gives you a P to the power of n by 2 dependence, and this part gives you a P to the power of n minus 1 dependence. So, this you gave P to the power of n by 2 minus 1 dependence. Okay. And then of course, since LD0 and F0 are connected, we can connect these two also, and that gives you a P to the power of n minus n by 2 dependence. So, you see that burning flux always increases with pressure as long as n is positive, which is the case. So, burning flux always increases with pressure, but you see that there is in the burning flux you also have density built into it. Okay. So, it also increases because you have lot of because your gas is more dense. So, it's more mass is consumed, more mass flux is consumed, that is why it is dependent on pressure. When you take off the dependence, when you take off the density, this burning flux has a n by 2 minus 1. So, whenever n is only greater than 2, then it becomes, when n is equal to 2, it becomes pressure insensitive, and if in other cases when n is equal to 1, then it actually decreases with pressure, as we will see later that SU actually decreases with pressure, whereas F0 is actually increases with pressure. Whereas the flame thickness, that is LD0, that has a clear negative dependence, because omega b appears in the denominator in this case. So, in that case we see that Pn by 2p is actually, so F0 is goes up with pressure, this can go up or mostly goes down with pressure, whereas this definitely goes down with pressure. Okay. LD0, there is a flame thickness corresponding with pressure. So, higher the pressure is, that the flame thickness becomes smaller. So, this gives you an idea about the challenge in computations also, because you see gas turbine engines or other engines, aero engines operate at high pressure, because when only we add heat at high pressure you can get work done, right. So, now of course, at high pressure you see that your LD0 reduces with pressure. So, if you do want to do a high pressure simulation, your flame thickness becomes very small. Okay, so you need more and more grid points, or if you are an experimentalist doing optical diagnostics, you need more and more camera resolution to basically image the flame thickness or solve for the flame thickness. So, this gives you a very challenging task to model flames at high pressure. So, as we have seen that implications, we have already discussed that for n equal to 2, f is not a function of pressure, and this is a cancellation between density and reaction, but this is not a fundamental result. Okay, for n equal to between 0 and 2, f increases with pressure, but SU decreases with pressure, which is mostly the case, and whereas L dependence of LD on pressure is through reaction, but not through diffusion. As a result of that, because lambda by Cp does not depend on pressure, okay, so as a result of this, your LD0 invariably decreases with pressure. So, with that we will end this class, and then we will go into analysis of the governing equations to derive the flame speed in a more rigorous manner. Here it was done in a more phenomenologically. Now, you can ask that why should you do it in a more rigorous manner, because then when you do things in a rigorous way, in a mathematically detailed manner, then all the properties of the flames also becomes much more clearer, and it will tell you also whether this analysis that we have done, whether that is correct or not. And but to gain more understanding, one needs to do a detailed rigorous analysis, which we will do in next class using the Frank-Kamenetsky analysis. For that, until then, thank you very much, and see you in next class.